All right, so first thing is like quick review here of what we did last week, okay? And that is that we talked about the law of conservation of energy, which says that in the absence of any non-conservative forces, air resistance, friction, things like that, okay, that energy, the mechanical energy of an object will not change. It will keep all of its mechanical energy from one point to another, converting it from potential to kinetic, but not losing any in total. Everyone all right with that idea? Okay, so that's what we talked about last week, and we said that that could mean the mechanical energy initial, which is the potential plus the kinetic, okay, will equal the mechanical energy final. Okay, so we remember we calculate mechanical energy by adding the two types, okay, and then we can solve for whatever it is we're missing. Okay, now question number 5's not that difficult, not sort of that difficult, the question where we had to do all that manipulating. It's a little bit more straightforward, and it involves a little bit of work-energy theorem, okay? Because it tells us we're using an average force of 40 newtons to compress a spring 0.1 meters. So they gave us a force and a distance. All right, so if we have force and distance, can we calculate the amount of work done on the spring? All right, that's going to be the mechanical energy of the spring ball system from there out. Okay, so right away we calculate the work done in the spring just by going 40 times 0.1, and we get 4 joules worth of potential energy in the spring. Okay, so sorry, that's the work done in the spring. What happens to the work done? It becomes mechanical energy. It becomes specifically elastic potential energy, which we don't really go over in Science 10. We talk about it more in Physics 20. Okay, if the spring is released, what will happen to this 4 joules of energy? Right. The spring will do work on the ball, transferring that mechanical energy, all 4 joules of it, to the ball. Now, that will mean then that the ball will have what kind of energy? Kinetic. Okay, so it's going to have 4 joules of kinetic energy, which is how we do E. Okay, we're simply going to say that for E, okay, we have the ball, and it has kinetic energy. We know that kinetic energy is 4 joules. We're told the mass of the ball is 0.01 kilograms. Okay, so we can solve for V. All right, so we just divide both sides by 1/2 of m, and then we square root. Okay, so we're left with this. V will equal the square root of 4 joules divided by 1/2 times 0.01. Okay, so we'll have 4 divided by 0.005, okay, because that's half of 0.01, okay, it gives us 800, and if we take the square root of that, we get 28.3 meters per second. Okay, so all I did was recognize that work was being done, that work would become mechanical energy of the system. That system can transfer that energy from the spring to the ball, so then the ball would end up with all 4 joules. And then I just did a kinetic energy calculation after that. Okay, so work energy theorem goes along with the law of conservation of energy. Once we put work into a system, okay, the system can do whatever it wants with it, but it's going to maintain that 4 joules or whatever amount of joules it is, that much mechanical energy. Everybody all right with that idea? Okay. Okay, so I would like you guys to try number 6 and number 7. Okay, so 6 is right there, and then try number 7 after that. Okay, so for number 6 here, we got an athlete who wants to jump, or who does jump, vertically upward from the ground to a height of 0.910 meters above the ground. Now, if I jump straight upwards, when I'm at my maximum height, how fast am I going? 0. All right, so at that point, the athlete only has potential energy. When they're on the ground and getting ready to jump, they would only have kinetic. Nope, not potential. They can't have potential if their feet are on the ground, but that's where they would be moving the fastest, so they would only have kinetic energy. All right, so it's still a law of conservation of energy question. Okay, it's just that we start out with only one kind of energy and we end with only one kind of energy. All right, so in this case, Okay, we have, we can start out with mghi equals, or sorry, not equals, plus 1/2 mvi squared equals mghf plus 1/2 mvf squared, just like we would for any other conservation of energy question. But since we're on the ground initially, there isn't any initial potential. And as we just said a minute ago, when you're at your maximum height, your speed is 0, so you can't have any kinetic energy. So what we're left with is the initial kinetic equals the final potential, right? And all we have to do is plug in or manipulate, plug in our numbers and solve. So we are looking for how fast, okay, they were going when they left the ground, their initial vertical speed. So I'm going to divide both sides by half of m. And what's going to happen to m? It's going to cancel off. Okay, it's on both sides. Okay, divided over, right? Because this would be true for any athlete, regardless of their mass. If they want to get to that height, they have to generate that speed. Okay, now depending on your mass, that means more energy, but they need to generate that speed in order to reach that height. So what we end up with is that V equals the square root of G times HF over 1/2. Okay, because the m's cancel. You can leave the m's in there. You can leave the 60 in there. It's not going to change your answer any. Okay, so we'll have 9.81 times 0.910, which was the height they jumped to, divided by 1/2, and then we square root all of that. Okay, so we'll have square root of 9.81 times 0.91 divided by 0.5. All right, so they'd have to be moving at 2.11 meters per second in order to reach. Whoop. Did I mistype something? I think I forgot to square root that. I think that 4.83 is the non-square rooted answer. I'll bet anything. No, I forgot to square root it, I think. $60 kilogram athlete vertically upward from the ground. Show vertical speed. Yeah. Oh no, I multiplied by 0.5. There's my mistake. I multiplied by 0.5. Okay. All right. So let's try that again. Bracket 9.81 times 0.91 divided by 0.5. That'll work better. There we go. 4.23 meters per second. Okay. All right. Questions on that one? Okay. Question number 7 is talking about a billiard ball propelled from a table at a horizontal speed of 1.5 meters per second, and the table's 1.30 meters above the floor. We're looking for the mechanical energy of the ball when it leaves the table. All right, so remember, how do we calculate mechanical energy? What two things do we add together? Kinetic and potential. All right, can we calculate those two for that ball? Okay, do it. Okay, so for number 7 here, okay, remember that we calculate mechanical energy by, not plus, okay, by simply adding together the potential energy plus the kinetic energy. Okay, so for this question here, that's going to mean 0.3 kilograms times 9.81 times 1.3 meters plus 1/2 times 0.3 kilograms times 1.5 squared. Okay, so 0.3 times 9.81 times 1.3 plus 0.5 times 0.3 times 1.5 squared. All right, so we got 4.16 joules worth of mechanical energy. Right? It's not very much because not very big, not very high off the ground, not moving very fast. Okay, so it doesn't have many of the ingredients to have a lot of energy there. Okay, so we'll skip over that. And okay, now for essentially kind of real world objects, okay, if I throw an object, okay, and I throw it straight, what does it naturally do? Yeah, it arcs, right? It arcs down to the ground because of gravity. Okay, all projectiles follow an arc, including satellites. Okay, when we put a satellite into orbit, all we're really doing is making it a projectile. We're making it go really, really fast, and it's always falling back to Earth. But it never gets closer to the Earth because the Earth is, well, not so much turning, just round, not flat. Because people who think the Earth is flat are crazy. Okay, I'm putting that out there on YouTube. People who think the Earth is flat are crazy because they are. Okay, now if something orbits the Earth, it's essentially a projectile that always falls. But because the Earth is round, it never gets any closer to the Earth. So it's always falling, but the amount the Earth curves away is the amount that it falls. So it moves in this circle. Okay, nearer to the Earth's surface, objects obviously arc back towards the ground, including, okay, anything we throw, anything we shoot, okay, like an arrow or a bullet or anything like that, they're always going to fall down towards the Earth. We have to take that into account if we're trying to hit a target. Okay? If your target is any significant distance away, you have to aim above it. All right, and we see that, okay, like if you're, even just playing catch with somebody, unless they're really close and you throw it really hard, okay, you're not going to throw it right at their glove. You're going to throw it above, and it's going to arc a little bit and come back down. Okay, people who are, trying to hit a target with an arrow, same deal. They're going to aim a little bit above. Okay, snipers, marksmen, whatever, they have to aim a little bit above. They simply adjust their scope so that the scope is pointed down the barrel. Okay, that way they have to lift the barrel up in order to get the target in the scope or in the crosshairs. Okay, and then when they pull the trigger, it accounts for, okay, the fall of the bullet during travel. That becomes a lot bigger issue the longer the shot you're taking. Okay, so if we're talking about the Canadian sniper who holds the grisliest world record, the longest kill shot, okay, it was just under 4 kilometers. Okay, ridiculous, like it's absolutely ridiculous that you could hit a target, okay, a person who was moving at that distance. Okay, and he had to account not only for the drop of the bullet, there was wind as well. His spotter had to give him windage so that he could account for how much the bullet would be pushed left or right during the shot, and it's crazy. Curvature of the Earth, rotation of the Earth, yeah. Okay, flight time of the bullet is more than a couple of seconds, and you've got a lot of factors you need to take into account. Okay, it's pretty crazy. Okay. All right, here's the next situation. You can draw this one. I want you to try it. We did a couple like this on Friday. Okay, so I have a roller coaster with a mass of 1,600 kilograms. It is at the top of its first hill that is 50 meters above ground level. And at that point, it is moving at 5 meters per second. I want you to calculate how fast it's going on this lower hill where it's only 8 meters above ground level, assuming, of course, energy is conserved. Okay, so I'll give you a few minutes on that one. Okay, so remember that you do want to start it out like this. The mechanical energy up here and the mechanical energy down here are equal. Okay? What's different is how much is potential and how much is kinetic at each point. All right. See how many of you remember how to do that from Friday. All right, so first thing we want to do is set it up as a law of conservation of energy question. So we got initial mechanical energy equals final mechanical energy. Now, we calculate mechanical energy by adding together potential and kinetic. Okay, does it have all of those? Like, are any of those 0? Can I cancel any of them? Okay, it's got potential energy initial, it's 50 meters above the ground. It's got initial kinetic because it's moving at 5 meters per second. So both of those have an actual value, not 0. Okay, and then final potential, it's got some of that. It's 8 meters above the ground, and we have to assume it's moving, or they wouldn't be asking us to calculate the final velocity. Okay, so there must be a value for EK as well. So I can't cancel any of those off. None of them are 0. Okay, what I'm looking for is part of which term? Like I'm looking for VF, so that would be part of which one of those terms? EKF, right. So before I get all the numbers and all the letters into this equation, I want to isolate that. Okay, so what do I do with EPF? Subtract it over to the other side. All right, so I'm going to have EP initial plus EK initial minus EP final equals EK final. All right, now I'm going to put in all of my formulas here. So I'll have M times G times H initial plus 1/2 MV initial squared minus M times G times H final equals 1/2 times mass times V final squared. Okay, so now all I've done is expand and put the formulas in. So I want to get VF by itself. What do I have to do with the 1/2 of M? Divide it over to the other side. Right. Okay, that leaves me with VF squared. I just want VF, so what do I do? Square root the whole thing. All right, so now I'm solving for VF. Not any different than what we did for like the high jumper question, okay? Like when we were trying to jump up to 0.91 meters, we're doing exactly the same thing. Only difference is that we've got all the forms of energy instead of just one. So it looks more involved. It is a little bit more involved, but the principle is still the same. All right, so when we plug in our numbers here, okay, and in fact, at this point, do I need to have all the M's in there? I can get rid of them if I want to. If I'm not comfortable with that, then I can leave them in. It's not going to change my answer any. All right, so I'll say 1600 times 9.81 times 50. So there's my initial potential energy, plus my initial kinetic, which will be 1/2 times 1600 times 5 squared. All right, so initial kinetic, plus, or sorry, not plus, minus my final potential. So that'll be 1600 times 9.81 times 8 meters. And I'm going to divide that all by 1/2 times 1600, because that's what my formula says to do. All right, now I would not try to enter this all in with brackets and everything else, because you're probably going to make a mistake. I rarely get it all right with all the brackets. Okay, so I just do it one piece at a time. So 1600 times 9.81 times 50. All right, plus 0.5 times 1600 times 5 squared. All right, minus 1600 times 9.81 times 8. Okay, divided by 0.5 times 1600. I could have just written 800 as well, but all right, then I have to square root that. All right, so when it gets to that point, it'll be moving at 29.1 meters per second. Okay, so yes, there's a lot of numbers in there. There's a fair amount of algebra in there, but when it comes right down to it, it's always the same set of steps. EI equals EF. Put down the forms of energy, cancel any off, plug in the formulas, manipulate for what you're looking for, and solve. Okay? It's always going to be the same set of steps. Okay? It just takes practice. Okay, we got time for practice. Your unit exam's not till Monday. Okay, so it's a week from today now. Plan for this week, guys. We're gonna look at conservation of energy today and tomorrow. Wednesday we'll do our lab. Okay, Thursday I'll do a unit exam review, and then Friday we'll see what else we need to work on. We still have to cover efficiency. We haven't covered that, so we may do that on Friday. Okay, efficiency is pretty easy though. Yeah. You guys would have done that in grade 9, but we have to review it again. Okay, and then Monday I'll have your unit exam. Okay, then we'll start into unit 4. Unit 4 is global systems and energy. That's why I leave it for last. Okay. There's a unit exam for that unit, yes. Okay, but we'll have lots of time. Right now, looking at it, guys, like I've taught that last unit in as little as 5 days. Okay, yes. Okay, and there's basically only 2 things in it that actually carry over into any other science course in high school. So that's why I can teach it in 5 days if I have to, okay? But we've got 2.5 weeks to go over it. So we'll easily get through it, have a unit exam, and have like 3-4 days for final exam review, okay? So we're all good. We're all good in terms of time and scheduling and all of that, because I look at that like the whole semester through. Okay, oh, we're 2 days behind. Oh, we're 5 days ahead. We're like easily 4 or 5 days ahead right now, so we're good. Okay, we got lots of time. So just know that's kind of where this week is going to go and where the week before Christmas will be going. Okay, we'll have a fair amount of things to cover that last week before Christmas, and then the week when we come back. Okay, then you'll have a unit exam and then a final exam review. Okay, so we're all good. We got lots of time. Okay, let's try another one here. Try this one. Write it down. Okay, it's a good example. It's just like what you just did. Okay, it's a law of conservation of energy question, except instead of a roller coaster, it's a toboggan, because it's winter. You're not riding any roller coasters right now, probably, but you might be sledding down big hills. But don't be like the kids I saw yesterday who were sliding down this hill the snowplow had made onto the road. Okay, like that was Darwin Awards City. Okay, don't do that. Okay. Okay, so here's the situation. Okay, maybe the hill's not that steep, but it's there. Okay, and here's the toboggan. I chose a toboggan because I can't draw, and it just looked like a candy cane, so I can draw that. Okay, all right, so we got the toboggan up here. Okay, and it says at one point it's 30 meters above the bottom of the hill and moving at 14 meters per second. Okay, shortly thereafter, the sled is moving at 23 meters per second. So somewhere else on the hill, okay, we don't know where, probably not the bottom, okay, it's moving at 23 meters per second, right? We're looking for how far above the bottom of the hill is it at this point. Okay, so again, assuming there's no loss of energy, which they don't mention, so we have to assume that's true. Okay, we got EF equals EI. I don't know why I wrote it that way. EI equals EF. Okay, do we have both kinds of energy at both points? Yeah, we can't cancel anything. All right, so we've got EP initial plus EK initial equals EP final plus EK final. What we're looking for is part of EP final. So I'm going to subtract the EK final over here before I put any confusing numbers in. All right, so initial potential plus initial kinetic minus final kinetic equals final potential. All right, so I've got that. Now I can plug in my formulas. Okay, so we've got M times G times H initial plus 1/2 MV initial squared minus 1/2 MV final squared equals M times G times H final. All right, did I give you mass? Do you need it? No. Okay, that's why I didn't give it to you. Okay. I once had a class where I kept telling them you don't need mass, just cancel mass, just cancel mass. And then on the exam, I forgot to put a mass on the question. Okay. But I told them like 100 times, you don't need mass, you don't need mass. And most people just remember that. But I had a couple of kids who came up to my desk during the exam, Mr. Coderre, I think you forgot to put the mass on this question. So I'm like, okay, it's 100 kilograms. No light for a roller coaster? That's what I picked. Let's go back to their desk. Another kid comes up. Mr. Coderre, I think you forgot to put the mass on here. Oh, at 10,000 kilograms. Okay. I go back to the desk. There's a few people like snickering because they realize what I'm doing, and they realize it doesn't matter what number I get them, it'll still work. Okay. And the third kid comes up. Mr. Coderre, you forgot to put the mass on here. Yeah. I don't know, 100 million. And at that point, they're just like, that's really heavy. Yeah, that's what it is. I mean, it doesn't matter what number I give them. They put it in, they're going to get the right answer anyway. So while it was kind of maybe a little bit cruel, it was also kind of funny. And it didn't really affect because they could put in whatever number they wanted and it was going to work. So in this case, though, we're going to cancel mass off because we don't really need it. Okay, so we're just going to get rid of it. Okay, so now we're going to manipulate and try and get HF by itself. So really, all I have to do is divide both sides by what? by G. Okay, so I'm going to have G times HI plus 1/2 VI squared minus 1/2 VF squared divided by G equals the final height. All right, so when I plug in my numbers, that'll be 9.81 times 30 plus 1/2 times 14 squared minus 1/2 times 23 squared divided by 9.81. Okay, so we got 9.81 times 30 plus 0.5 times 14 squared, 14 squared, minus 0.5 times 23 squared, divided by 9.81. All right, so they will be 13 meters above ground level when they are moving at 23 meters per second. Okay. Are these starting to make a bit of sense? I mean, they are all the same after all, right? Like, we really haven't done anything different on any one of these. We set it up, we move stuff around, and we solve for the answer, okay? There's really not a lot of complexity to them, okay? It's mostly just remember the steps, repeat the steps, okay? All right, let me give you guys a little break. Give you like 3-minute break here, then we'll try the next one. All right, I'm not going to get into the solution of the problem, but I'm just going to like show you the setup of the problem here. So here's our cliff. Car drives off the cliff. Okay, it drives off this cliff at 25 meters per second. Okay, and then it does this and strikes the ground below at 53 meters per second. We are looking for the height of the cliff. Okay, now they've mentioned nothing about air resistance or friction, so we can assume energy is conserved. Unless we're told otherwise, we assume energy is conserved. Okay, for you guys, it's always conserved in Science 10. All right, give that, see if you can kind of figure that one out the rest of the way here. Okay, we should be able to cancel one of the types of energy here, okay, in this problem. All right, so next step is, okay, we set up our law of conservation of energy setup. Okay, listening please. So we got, initially, we've got kinetic energy because it's moving at 25 meters per second, and they're asking us for the height of the cliff. It's on the top of a cliff, so it's got potential energy. So we know that we have initial potential and initial kinetic. All right, down here, the final point, it's moving at 53 meters per second, but it's hitting the ground. So we know it's got kinetic energy, but it doesn't have any what? It doesn't have any potential at the end because when you're on the ground, you can't fall any further. Okay. All right. So what we have here is we plug in our numbers, m times g times h initial plus 1/2 mv initial squared equals 1/2 mv final squared. Now, I probably should have moved EK initial first. Okay, I didn't, but I can do it now, right? Because what I'm looking for is the initial height. So I'm going to move 1/2 mvi squared over here by doing what? Subtracting it. Okay, so I'm going to have m times g times h initial equals the final kinetic minus the initial kinetic. Okay, can I cancel the m's off? Yes. All right, so let's get rid of those. Okay, and if I want to find the initial height, I just have to divide both sides by g. And then I'm left with initial height. All right, so we'll have initial height equals 1/2 times, listening guys, 53 squared minus 1/2 times 25 squared divided by 9.81.
What are you betting on?
Okay, so the cliff is 111 meters high. That is a high cliff, but it didn't mean if it's not 100, if it's not over 100 meters, it's not really a cliff. It's, you know, yeah, it's got to be intimidating, right? Yeah. There has to be an element of fear and danger when you look over the edge. Okay, does that one make sense to everybody? All right, what do you suppose tomorrow's quiz will have on it? Yeah, exactly. So, whoa, I didn't say to pack up yet. Okay, there's still like 4 or 5 minutes left in class. Okay, so tomorrow's quiz will have a conservation, actually it'll probably have 2 conservation of energy problems on it, so make sure you look at those tonight and give them a try. Okay, remember also that your work lab is due this week. Okay, you need to make sure you have that one done. Okay, that was the rubber band one we did, so make sure you have that one done. All right, unit exam is coming up. I think I posted the review already. We'll just double check here. Okay, but I'm pretty sure I put it on Google Classroom last week. Oh, and something happened with my post for Friday. It didn't come out. It was set to private or something, and it didn't come out. So I put it up there, okay, in case you missed it. Okay, so here it is, December 3rd. Okay, I put the unit exam review up. All right, we'll do a formal unit exam review this week, but I do have the review package up there. It's got a bunch of different questions that are, old exam questions, things like that, so you get some idea. It doesn't have a multiple choice practice test like the others, just some problem solving stuff. All right.